In this video, we will show you how to use the XY mode display. In order to do that, we have connected two synchronized function generator outputs to channel A and channel B of our Mega 1 device. With this setup, we are going to create some basic Lissajous patterns. You can find the XY scope under the Displays tab. Analog generators are set to 1 volt sine, so we will not exceed the 2 volts that are set on channel A and channel B. We have also set a trigger on one of the channels, so the signal waveform stands still on the screen. We have set the time-based setting long enough in order to see the waveform clearly enough. With synchronized outputs from analog generators, we have two identical sine waveforms of 10 Hz in frequency and 1 volt in amplitude. We have set the frequency low enough so we can see the digital beam travel across the screen. In oscilloscope mode, the signal represents the relationship between data according to time. In the XY mode, the signal represents the relationship only between the data on the two oscilloscope inputs. As the name suggests, it's X to Y. The vertical axis represents data on channel A, and the horizontal axis represents data on channel B. When the signals are the same in amplitude, frequency and phase, the voltage on channel A will drive the vertical position of the beam up and down, and the voltage on channel B will drive the horizontal position of the beam left and right. The sum of that movement is the waveform jumping from bottom left to top right quadrant of the XY scope display at exactly 45 degrees, while the amplitudes are equal. When the signals are different in phase, the path of the beam will change in fairly predicted ways, as we will see right now. Let's increase time base a little so we can see the full path of the beam. Here is previous example of the pattern when the signals are lined up in phase and amplitude. If we decrease the phase towards -90 degrees or 270 degrees, which is actually the same position, the signal will form into a nice circle. When we decrease the time-based setting, we are able to see the beam travel counterclockwise at 270 phase shift. At 90 degrees phase shift, we can see the circle being formed clockwise. If we set the two signals back in phase, the beam will form a line. If we do the 180 degrees phase shift, the pattern will form the exact opposite line at 135 degrees. Decreasing the phase shift towards 90 degrees will form a circle pattern again. Switch to sync will get us where we started. Now let's see what happens if the signals are different in frequency. If we increase one of the channels to 20 Hz, the other is still at 10 Hz, which represents 2:1 ratio, it will form a figure 8 pattern. If we decrease the same channel to 5 Hz, which will now represent a 1:2 ratio, the signal will turn into this horizontal figure 8 pattern. At 3:1 ratio, that's 30 to 10 Hz, the waveform gives us 3 regions and 2 connections. At 4:1 ratio, that's 40 to 10 Hz, the waveform gives us 4 regions and 3 connections. At 5:1 ratio, that's 50 to 10 Hz, the waveform gives us 5 regions and 4 connections, and so on. Slightly greater frequency than 10 Hz gives us a rotating circle in the one direction, and slightly lower frequency will give us a rotating circle in the opposite direction. In this video we showed you how to use the XY mode and Mega1 plugin to observe Lissajous patterns. The XY mode is a useful tool everywhere we need to track phase differences between multiple input signals, including component characteristic, broadcast engineering, audio engineering, and other various fields. Thanks for watching.